begin this session here. My name is Søren Landa. I'm a senior associate professor here at the Department of Engineering, and I'm chairing this session here, and I'm also chairing the assessment committee. And of course, I'm very glad about that, because such a Ph.D. defense as we're having here today is a day of celebrating the academic tradition. Maybe you don't feel so much joy right now, but you probably will later. And of course, our Ph.D. candidate here, Kim Arild Steen, is going today to defend his Ph.D. thesis entitled Pattern Recognition Methods for Reduction of Human-Wildlife Conflicts. And also I know and would like to acknowledge Kim that to do and submit a PhD, that's a hard work, and sometimes a lot of frustrations also. And I guess you have experienced both things through the last couple of years, but still managed to arrive at this point here of the defense. Okay, so I would also like to welcome our assessment committee's two external members. We have here Professor David Anderson from Georgia Tech University in the United States. You're from the School of Electrical and Computer Engineering, and a professor in Computer Systems and Software, Bioengineering and Digital Signal Processing. Yes, and also we have Henrik Ornes from the Department of Applied Mathematics and DTU Compute from Technical University of Copenhagen. Technical University of Denmark it's called, not Copenhagen, but it's in Copenhagen, and you are associate professor here. And during your studies, you have been enrolled or employed here at the Department of Engineering, and you've had two supervisors. You have the main supervisor, Henrik Karstoff, Professor Henrik Karstoff here, and we have another supervisor here, senior researcher Ole Gren. Also, I would like to welcome all of you in the audience. It's always very nice to see that so many would like to come and share this session here with us and watch how people is performing. Very nice. Okay, so I have a note here saying that such a public PhD defense here, as I mentioned, is an academic tradition to have that, and along with such a traditions, there are some rules. So I would just like to mention the rules and regulations we have for what's going on here today. So when I'm finished with this introduction here, I will ask him to give a public presentation of his work, and it should not last much longer than 45 minutes. After that, we will have a short break. You are allowed to walk away, but I hope most of you will return back after the break and still hear the discussion afterwards. And then the two external members of the assessment committee will ask questions and discuss the work by Kim. And the rules is stating that in total, both this presentation here and the questioning afterward is not allowed to have a duration longer than 3 hours. So we have a closed deadline here in this afternoon. Of course, also Kim can take questions from the auditorium here. So if any one of you are interested in asking Kim a question or two, you can do that, but I would like to be notified if you have a question. So if you have a question, maybe in the break you can approach me and say you have a question. And also the rules are stating that a question ex auditorio, as it's called, and Kim's response cannot take longer than 15 minutes in total. So many rules to remember here. Okay, and then finally, when this is all finished, I would like to remind you that there is a reception afterwards in room 101, I think it is. So it's downstairs here, and I guess it will be around 3:30 or something like that. It will be able to start here. And during that reception, of course, then the assessment committee will come in and announce the results of the assessment. Okay, so I think that was the word I would like to say here at the beginning. So I would like to welcome Kim to give this presentation.
Yes. Thank you. Yes, as Søren said, this is a presentation of my Ph.D. project, which I've entitled Pattern Recognition Methods for Reduction of Human-Wildlife Conflicts. Most of the work has been done here at the Department of Engineering, but I've also been abroad at the Georgia Tech, where I did some of my work. So this is the overview of my presentation today. First, I'll introduce two specific cases of wildlife conflicts within the scope of agriculture. I'll talk about why this is a conflict in the agricultural perspective, but also why it's interesting to look at this from a scientific and engineering point of view. Then I'll talk about my work within the adaptive frightening device, which has been motivated by one of these conflicts between the agriculture and large flocks of birds. Then I'll talk about another conflict during mowing operations, which I entitled wildlife-friendly farming, where I'll talk about how I've been working with sensor technologies and methods to reduce conflicts during these mowing operations. And in the end of my presentation, I'll summarize this presentation and my PhD work, but also give some suggestions to future work within this context. So moving on to the first conflict I'm talking about. In agriculture, there's a huge demand for high efficiency farming. This is because there's a lot of competition in the agricultural sector, but also because there's a huge demand to provide food for a growing human population. So, and besides that, we have an increased population of a lot of different bird species that includes especially geese. So agricultural production experience a lot of conflicts with these large flocks of geese because when you have a large agricultural production, you don't really have the time to go out and scare away these birds all the time on your very big field. And there's also a lot of birds that need food, so these two things collide. So these birds, they damage the crops, they could also eat the crops of the farmer, they can also eat livestock food supplies from the farmer. This is an economic challenge for the farmer. And often we rely on using frightening devices to solve these problems with the birds. However, existing systems that we use right now, they experience habituation, where the birds get used to the frightening and no longer respond to that. So I'll come back to that later in the presentation. Another conflict is during mowing operations, where we again have an increased demand for efficiency in the agricultural production. So we have very wide working widths of the machinery, but also high working speeds. And at the same time, during these mowing operations, we have small animals hiding in the grass, nesting or seeking cover. And this makes it very dangerous for the animal, because the farmer really doesn't have any ability to spot these animals during these operations. So a lot of animals are being killed or injured each year due to this. This, of course, is not good for the animal, but it also imposes mental stress on the farmer that needs to go out and do mercy killings on these animals if they're heavily injured. But also, it could also impose health hazards, because if you use this material that you harvest or that you mow for livestock food supplies, then the livestock could be infected with bacteria from these dead animals. And it's an increasing problem, because we're increasing the working widths of these machineries. So here the problem is that the animals, they hide in the grass and we are not able to spot them. So how can we develop sensor technologies that could help aid us here? So moving on to my work within the adaptive frightening device. And here I'll present the framework for realizing this device that I proposed during my PhD, and discuss some of the methods and results to implement this. I said at the beginning that existing frightening devices experience habituation. And this is the process where the birds get used to the frightening stimuli that we're trying to apply. This could be a gas exploder that gives off a large bang. But after a while, if these large bangs just comes randomly, or even timed, or even randomly, then it just becomes a part of the soundscape and the background soundscape, and the birds are no longer afraid of that. The problem with this is that it's triggered with timed or random triggering. So the scaring becomes non-specific. Rather than just being an event that happens when the birds are in the area, it's something that's always there. There's been some work regarding using bioacoustics as the frightening stimuli, and it has been shown that the birds are less likely to habituate to this. Just to explain that bioacoustics is the internal communication between the birds. So it could be that you play a sound that is the alarm or distress call of this specific bird. And this also to target a specific species. But again, if you just play this sound, not thinking about who you're playing it to and when you're playing it, then you could also experience habituation, and experiments have shown that. So I propose a framework. This works around this model that we have a sense, reason, and act. So if we can sense the presence of the birds that we want to scare away, and we can reason upon that, then we can act accordingly. The building blocks of this framework is, of course, we need to detect when we want to scare the birds away. So we need to detect the presence of a bird. But as I said, the bioacoustics is a species-specific signal that the birds use to communicate to each other. So I also suggest that you have some kind of species recognition within this framework, so you're able to recognize which species you're actually trying to scare away. The end result of this is a change in behavior. We want to change the bird's behavior from landing or being on the ground to escaping from the fields. So if we could recognize the behavior automatically, we could use this in an intelligent way to respond to what we see. And then the last block is decision of action. So based on this knowledge, this one decides what action to take. Should I use the same acoustic stimuli as I just previously used yesterday, or should I try something else? So in that way it becomes adaptive. So which sensors could you use to implement such a system? Well, they have to be non-invasive, because you can't really attach sensors on these animals because they're living wildly. It has to be cost efficient, because you need to cover very large areas. And as imposed by the framework, these sensors has to enable recognition of species and behavior. In my PhD work, I've been working with two different sensors for this. It's the microphones. They are cost efficient, non-invasive, and as I'll be talking about later, they also enable audio-based species recognition. So we can recognize species based on what we hear. I've been working with cameras. They are also non-invasive. You're able to record the animals from a distance. And cameras or visual technology have been used in a lot of applications for behavioral research. So acoustic pattern recognition is a major part of my PhD project. So just to give a short overview of what that is. So we have an animal here, and I can say that much, that it's a goose. And then it vocalizes. And we detect the part of the signal that we want to analyze. So this is a continuous waveform of that this bird has vocalized. And to use this waveform and be able to say which kind of bird it is, we need to calculate some characteristics of this waveform. So here I've shown some of the basic components of a feature extraction method called the MEL frequency cepstral coefficients, which is a method being used in a lot of human speech recognition. And the result of this is a representation of this of a small part of this by a couple of numbers that we call feature vectors. So using these features, we can apply a model. This shows as a statistical model, but we can apply any kind of rule to these features. And if we have labeled data that we know that these features come from this kind of species, we can use this to classify that this is in fact a barnacle goose. So onto this model. In my work, I've been working partly with the Gaussian mixture model. And here we have an illustration of this. We have features from one species, there's a blue, and from another species, there's a red. So we have two classifiers, we say. So the model of this is a mixture of Gaussians. So you have the Gaussian distribution here, and it has some parameters. So it has the mixing coefficients and the mean and covariance of these models. And the way we do this is that we have labeled data, and we train a model based on these labeled data and find the parameters for these models. And once we have that, then when we need to do classification, we can calculate real acoustic features of the waveform that we are just recording. And maybe we record a longer period of time, and we have a couple of feature vectors that in this form we have a matrix of features. And we can use that to calculate the likelihood, or as shown here, the log likelihood of this vocalization belonging to this species or this species, and thereby classify which species that we're looking at, or hearing. So this could be used for detection, but also of species recognition. And the reason that is that the flock of birds, they use acoustic communication within this in the flock, and this communication is species specific, and we can record it from a distance. So so we can cover a large range, but we can also do that without seeing the birds. So we can cover difficult or different kinds of fields. But of course, acoustic detection in outdoor environments could be difficult because of background noise and also very diverse soundscapes. So here's the model from a paper about body-based detection and recognition of these conflict species. So the way we do this, we record a vocalization and extract the features that we want to look at. And then we have a model of all the conflict animals that we're interested in being able to scare away. And we compare that to a background model. So this background model, it could be a Gaussian mixture model, right, like this, explaining or representing other sounds that we're not interested in recognizing. So it could be dogs barking, cars moving by, or other background sounds. And once we classify this as a conflict animal, we can go into the individual species recognition and see what's the likelihood of this vocalization belonging to a grey-lag goose or a pink-footed goose or some of the other bird species that we tested in this paper. So here is shown more graphically that we have, first we have this blue feature, so this data is the conflict model and the background model. And based on this, we can calculate the probability of the sound coming from a conflict species or not. And then moving on to the individual classifications. So you could do this with just one step or one model. But the good thing about this is that you can design a classifier for this part that is good for performing this, and you can design a classifier that could perform better here. So some results using this. So this is this shows the detection of conflict species that we are testing against a background model. So as you can see here, when we have higher signal-to-noise ratios, we have a pretty good detection of these conflict species. But as the noise increases, the signal-to-noise ratio decreases, so does the performance. So this needs to be solved if the system should not trigger or play back a sound all the time, and thereby maybe experience habituation. And this is the recognition of the individual species. As you see here by the bold numbers here, that shows the detection rate of the specific species. And this shows pretty good performance. But here we don't impose noise on this, so it's pretty high signal-to-noise ratio. And as we saw here, we would expect that the performance decreases as the signal-to-noise ratio decreases. But maybe that should not be such a big problem, because maybe we should just know if it's highly likely that these two birds are in the area, so we can respond to these two birds, or maybe even that's highly likely that we have 3 different kind of species in the area. But the best results, of course, would be that we know that 100% that this one was in the area. So this was the acoustic detection and species recognition part of the framework. Moving on to behavior recognition. Well, as I said, the flock use acoustic communication within the flock, and they use this communication to interact during certain behaviors. So that they are telling each other, this is a good place to land, we should go here and eat, or now we need to go away. They use their own alarm and distress call to warn each other that they should go away. So we can use this recorded information to actually recognize between these behaviors. The good thing about this is it's cost efficient. We use microphones and we don't need to be able to see the birds. But again, in outdoor environments we could have problems with background noise. So the way we did this was to put out a system that recorded wild geese on a field on the west coast of Denmark for a little over 1 month. And we got 2 days of incidents of these behaviors. So we didn't have a lot of data. So instead of trying to model a distribution as we do with the Gaussian mixture model, we use something called support vector machines. And these are less sensitive to limited data as the Gaussian mixture model would be. And here, instead of modeling the distribution, we model the decision boundary between the classes. And in the support vector machine, we do this by maximizing the margin between these classes. This shows a linear separable case where we can divide the classes by just a line or a plane. But data is always, it's very seldom linearly separable. So you could use kernel functions to implement this support vector machine to handle nonlinear data as well. And we use this in this context. Well, as you can see here, this is again with a pretty high signal-to-noise ratio because we want to see if this was possible or not. As you can see here, the precision of flushing behavior, it's classifying some of the data as landing behavior, and if you calculate the precision, you get 0.66. But this is not that impressive, so it needs to be improved in order to work efficiently. So how could you do this? Well, you could add more information. So here's a video of geese landing. And you can hear the soundscape. Now they're foraging. And flushing away from the field. So you have a very clear soundscape. I don't know if you could hear that, but you could see that the behavior changed. So we could add more sensors to this problem and still use the audio-based recognition, but add visual-based recognition as well, and classify these behaviors individually, and in the end fuse these classifications to hopefully achieve a better result. So we did this, and if you see here, this is the same as you saw before. We have the detection rate of flushing behavior. And this is audio and video. So you see here that using audio we could detect flushing behavior 70% plus minus 20% accuracy. But if you fuse it with video, we could achieve better results. So we have fused them using 3 kinds of rules, sum, product and mean rule, and we could improve the performance. You can see here that the video-based classifier is pretty good at detecting this kind of behavior. But if we move on to landing behavior here, we can see that the video-based classifier here, it's not that impressive. But if we use some information from the acoustic recognition, we can improve that performance as well. However, using cameras is not really that practical in outdoor environments, because you have dusts, you have different weather conditions, but the major part is that you need to cover large agricultural fields, and you have a limited view with these camera technologies. But the idea of using the movement from the birds to recognize behavior rather than the soundscape is pretty nice. So how can we achieve this in another way? Well, you could use arrays. So if we have an array of microphones, we can localize and track these birds instead of video recording them, and thereby monitor both the presence and also behavior of these birds. So we use the best from the audio, that we are able to detect the birds from a long distance, and we could base a recognition on movement. So we can monitor large regions, but this of course complicates the infrastructure, because we have multiple sensors in this environment. So how is this possible? Well, if we have an agricultural field here, and we place microphones along the perimeter, we have a 200 by 200 meter field here, and we have an acoustic source within this field. It emits an acoustic signal, and we calculate the energy of this signal at each microphone. And then based on the energy ratio between microphone pairs, we can calculate these circles where the acoustic source is highly likely to be. And the intersection of this is actually where the source is. And if you transform these circles to a cost function, as we see here, we see the contours of a cost function, and the blue indicates the lower values of this cost function. And if we minimize this cost function, we get our estimate of the position, which in this case is actually right on the target. But what happens if we experience noise? Well, here I selected 4 random microphones which are subject to noise. And as you can see here, these circles, they move around and move away from the actual position. And you can see here, if we minimize this cost function, we get an estimate that is very far away from the source. And the reason for this is that if we draw these lines here with respect to how important they are in this cost function, so these 3 lines, they have the lowest cost, or the highest probability of the source being there. You can see that we have this line here, and it affects our estimate. But we have a lot of information here that we could use. So instead of using what was shown here, a quadratic cost function, where we use the least squares algorithm to localize, we could fit our cost function with this, where we have a sub L1 norm in our cost, and thereby all of these circles would have a contribution to our initial estimate, or a final estimate of the position. And here we see the contours of this cost function, and in this case we have an estimate pretty close to the source. So using this, and using a particle filter which is called the cost reference particle filter, it's a particle filter that's able to use user-defined cost functions to evaluate the particles within the filter. We could track 10 acoustic sources that were positioned in a flock. So in a flock means that the position of the birds were simulated with a 2-dimensional Gaussian distribution with different sizes. So you can see here that the area of the flock is increased here along the x-axis. And you can see here the tracking error using the least squares method, or the new cost reference particle filter with our modified cost function. And as you can see here, even if the flock is large in area, it's still 10 sources, but even if it's large in area, we get around the same error, but the least squares estimate is worse. And this is of course in the presence of noise. Algorithms and mathematics is no good if we're not able to scare the birds away. So we did a preliminary field experiment where we put a system out able to recognize behavior of barnacle geese just based on the acoustic soundscape. So no array design and no camera aiding us here. And we turned on the system for 3 weeks. And you can see here, this is the active period number 1. This is the red bar here. And this graph shows the measured goose activity. So we measured the goose activity by counting the goose droppings along 3 lines from the scaring device. So you can see that there's no activity near the scaring device. Then after 3 weeks we turned off the system to see if the area was not good for the geese, if they just didn't want to be there. But as you can see, when we turned off the system, the activity increased. Then again we turned on the system to see if we could scare the geese away now, because they have now grew accustomed to that area. There was nice food and there was water. But as you see, when we turned off the system, or on the system, goose activity dropped again. So this was a period of about 5 to 6 weeks where we had the system turned on. And if you compare with gas exploders, you get a maximum 2 weeks time where the system is good at scaring the birds away before you have to do something. So, moving on to my work within wildlife-friendly farming. Well, as I said in the beginning of my presentation, we experience these problems during mowing operations, that these small animals, they hide in the grass. And existing methods to solve this is that you use trained dogs or plastic bags to either search for the animals prior to mowing, or you put up scaring mechanisms prior to mowing to prevent, so you think that the animals would move away from the field. This is very time consuming and therefore very inefficient. Another way is this bar here that's being handheld, where you have infrared detectors looking down in the grass. This is actually an efficient way of doing this. It detects the animals, however it takes a very long time, so it's inefficient in an agricultural perspective. However, the idea of detecting these animals is pretty good, but if we could do it automatically while we do the mowing operation, we could maintain efficiency instead of spending a lot of time prior to mowing. And thereby we could reduce mortality as they did with using this system. But also we could document the incidents if there were any. And this could be good knowledge for the farmer, for quality insurance, but also for biologists which are interested in this problem. So the Wildretter project used infrared detectors, but now we also see a lot of commercial available thermal cameras. And the thermal camera has a nice property, because as you can see here in the visual domain, if you didn't see this image before, it would be really hard to spot that there's actually 2 animals hiding in the grass here. Especially if you're moving with 15 or 20 kilometers per hour, then this becomes a really hard problem. But in the thermal image, you can actually see that the temperature of these animals really gives them away. So we can maybe use this in an automatic system. So we tested this by putting a thermal camera on the hood of a tractor and recorded a chicken, or hen as shown here, and a rabbit, which were hiding in this grass. And we had them in a cage so they wouldn't be run over by the tractor, of course. And we recorded it with a thermal camera to test our hypothesis. So this is a video showing the detection. So you can see here, this is a thermal image. Blue is hotter. And here, this white dot shows that we believe that this is an animal because of the temperature. But as you can see here, we also have grass patches here which are warm. And as you can see here, over here in the detection, we have some white dots there and there, which we believe is an animal because it's a hot area. So it's possible to automatically detect these hotspots But if the animals are hiding in very dense grass, we have some problems. However, we also saw that we recognize other hot objects, so we are very sensitive to false positives, just basing our detection on the temperature. And these experiments, we have a very limited field of view, and this of course means that you spot the animal very close to the machinery. This puts very high requirements on the reaction time of the machinery or the farmer. So how can we solve some of these problems? Well, a guy called Martin Israel from Germany, he also looked at this problem, and he eventually ended up looking at these animals in the grass from a top view image. Here he used a drone flying over the field to spot these animals, and he concluded that it's possible to spot these animals from a very high altitude. However, it was done manually, so it was still pretty time consuming, and it was also sometimes very difficult to spot the difference between what was not an animal here and what was an animal. And a part of this problem was, of course, as maybe you can see here, that the detail level in the thermal images is not that high, so you don't have a lot of detail. And this was because the signal was compressed when it was sent from the drone to the base station, which recorded the thermal image. However, the idea of looking from a top view, like this system, is a pretty good idea. But how could we remove some of these defects, the vibrations of the drone, and also the compression of the thermal image? Well, we built our own, or we rented our own system, where we put a thermal camera and a visual camera next to each other, because maybe we could gain some information from this guy as well. And we put a drone up here for comparison. This system enables us to record animals which were located here in the grass from 3 meters to 40 meters up in the air with uncompressed thermal data. So here's an example of this image. As you can see here, we have, this is an animal, this is a rabbit, a chicken, and this is a rabbit. And here we have a molehill that's being heated by the sun. So if you use just temperature to recognize between these objects, that you classify these three as animals. But we don't just want to see that this is an animal and this is an animal. So how do you classify between these? Well, as we saw in the acoustic recognition, you could use features to classify between objects or species. And during this Ph.D. work, we looked at how to extract features from these thermal objects. We came up with a way of extracting the contour of these thermal images, or these thermal objects, and calculating the mean temperature of this contour, and shrinking the object with the same contour, and thereby calculating the contour until we reach the middle of the object. So, to show this in another way, we have this object here, which, if we calculate the mean temperature of these contours from the edge here to the center, we get this kind of thermal signature. And we also have this object, which gives us this thermal signature. So if we take this continuous function and parameterize it by 7 discrete cosine transform coefficient, we have a feature representation of our objects. So using this, we try to classify these objects that we saw from a top-down view. So the idea here is that a drone is flying over the field and detects these hot objects. But in order for it to be able to recognize between the objects, it needs to come closer. So even though Martin Israel showed that we could detect these objects from a high altitude, we needed more information at low altitudes to recognize between these objects. So this video that I'll show you shows a detection of these objects. We have an animal here and here, as you saw on the previous image, these two. And the green marks that we believe that this is an animal. And we do this by classifying using a k nearest neighbor classifier. And by doing this, we can calculate the probability of the current frame that this is an animal and this is not. And in the beginning, we think that this is an animal because it has a high probability of being an animal, and this has a low probability of being an animal. But we can build up this belief over time. So if you use more frames, then we can become more or less certain that we are dealing with an animal or not. And we build up this while we are approaching the animals. I'll show you this in the video. So, you see here. Now we detect this as an animal, and this is in fact a rabbit that we have here. And now we have the molehill here. Right now we think it's an animal, but if we give it time, then it eventually learns that it's not. So we got some pretty good results at low altitudes using this idea. And it motivates further work using this kind of method. So within wildlife-friendly farming, we've investigated a tractor model system and how we can detect these hotspots, but we are very sensitive to false positives here. And this of course motivates an ability to recognize between these hotspots in the thermal image, and we showed that using thermal signatures. And this was used in a drone-like setup using this big lift to detect and also recognize between these hot objects, which shows pretty good performance at low altitudes. So a summary of this PhD presentation and my PhD work is that I have applied pattern recognition methods to existing solutions to human-wildlife conflicts, and thereby try to improve that. Within the adaptive frightening device, we have made a system that's capable of adjusting the frightening stimuli to a specific species. So if we use bioacoustics, we could use their own distress call, but we could also use natural predators. The system is able to monitor the response to the stimuli and act accordingly, and adapt if it can see that the birds are getting used to the scaring stimuli. And this system also allows for reinforcement and variability in stimuli. You could add different stimuli and apply them in a different manner based on what you see or what you hear. But in wildlife-friendly farming, we show that investigated automatic detection, and this could reduce mortality during these mowing operations. And we have shown that you could use thermal images to recognize between these hot objects that we record. So the contributions of this thesis is a generic framework for detection and recognition of species, an automated recognition of behavior based on the audio, the soundscape that we are measuring, and the framework for fusing this recognition with visual information to improve this performance, and a tracking scheme for tracking acoustic targets within a long baseline array. So this array where we have a large distance between the microphones is known as a long baseline array. And here we've shown a novel cost function that's improving performance when we have noise in the array. Within wildlife-friendly farming, we have investigated tractor and drone-mounted detection systems and come up with a way to automatically recognize these objects in thermal images. And this is also part of ongoing work. But there are still some improvements that you could do. Within the frightening device, the adaptive frightening device, it needs to be more robust to diverse soundscapes. So here I suggest that using this Gaussian mixture model framework, you could implement incremental learning so that the models, especially for the background, could over time start to learn the soundscape of that specific environment that it's standing in. It also needs to improve robustness to background noise. And here I've shown that there's a possibility to use these arrays to detect and recognize behavior and thereby be more robust to sudden background noise. this array, of course, needs a real-time tracking algorithm to make this practical possible. And here I suggest using something called the interactive multiple model Kalman filter, which is a Kalman filter that uses multiple Kalman filters to enable tracking of a non-linear movement. And of course, more field experiments should be conducted because we want to increase the statistical power of these results. The results we have is only based on one system, and also based on only one type of birds, the barnacles. Within wildlife-friendly farming, work should be done to reduce the number of false positives, because every time we get a detection and a recognition of an animal, we need to do something to prevent hitting that animal. And this could be done with sensor fusion methods. We recorded visual images along with the thermal images, and maybe you can use information from that to improve this, as with the audio-visual recognition. But also improve this thermal signature extraction and have more animals. So we have more animal candidates, but also more non-animals, which we are detecting as hotspots. It could be heated stones, molehills, could be wood, it could be different kinds of hot objects that we detect. The drone experience should be done in controlled conditions, where we take the large lift out of the equation and put the system on an actual drone, being able to record these animals in real life applications. And last but not least, we need to develop strategies for what to do after we detect these animals, because it's good that we can detect them, but if you want to maintain efficiency, then we also need an efficient way of dealing with the detection of these animals. So it should be efficient. So, thank you for listening.
Okay, Kim, thank you for the presentation. And we will have a short break now and begin again at 2 o'clock sharp. So, yeah, just take the break now.
I don't care. Whatever they, I guess that's part of the protocol. So
Go up here again.
whatever you want.
And
Okay.
say it's time to continue this defense. Still a lot of people in the room. So that's very nice. Very much supporting you here. So
And they actually left during the break.
you can't cheer, but you can smile and support when the answer is very wrong. Okay, so I think we should just jump to the part where we're going to discuss the work. And our first opponent is David Anderson, professor at Georgia Tech, as I mentioned. His research interest is centered around audio and signal processing. I think he has almost 100 publications and have different patents in the area. So a big capacity here, and earned several distinctions. So I think I would ask you, Professor Anderson, to talk to Kim.
Okay. Good presentation, by the way.
Thank you.
Thank you. You've done a variety of things with your work. I'm going to ask you a few questions to start with about your background model. You, in your slides at the end, you mentioned that that's something that you wanted to improve. Is that your thesis there?
Yeah.
Okay, so I'm looking at page 33 and 34 if you wanted to
Yep.
wander over that way. Okay, great. Let's start on page 34. There's a table 2.3. And you had this, I think, in your presentation as well.
Yes. This one.
There you go. Okay. We have different signal to noise ratios here.
Yeah.
And I wanted, can you explain a little bit more what type of noise you added, why you chose that noise, and at what point, where it was added and how it was added?
So let me first say how it was done and then what was added. The way I did this, I divided my data into two parts, one for training and then one for testing. And the part where I used for training was data without noise, or data that the original data.
So I guess I should interrupt for a second. The data that you divided, is this the data that you collected?
That's the data from the paper. It's both the data that I collected, but also data from some sound libraries.
That's right.
Because we only collected data from the barnacle goose, and we wanted to test this on different species as well. But the data that I use for training, I trained these Gaussian mixture models on this non-noisy data, or the data we recorded in the wild, so there was still some noise present, of course. And then I imposed different levels of additive white Gaussian noise on the test data.
Okay, so and why did you choose white noise?
Well, actually, you could have chosen different kinds of noises, and maybe you should have chosen another type of noise to resemble the environment in the outdoor. I guess it was kind of a habit why I chose the white Gaussian noise.
So if you, what other noises do you think would have been a good choice?
Well, you could have added noises, of course, a wind gust that you record, so it would be very realistic. But you could also use different other sounds that you superimpose on the audio. So it could be background noises such as cars moving by or dogs barking, to get a more realistic environment for the test.
And on the the segments here that you classified, how long were they?
In this paper it was about half a second.
Half a second.
Yeah.
If you, how long does it need to be? In other words, how quickly do you need to recognize the species?
Well, actually, that's the good thing about this, is that we can spend a lot of time being certain that this is actually the birds that we're looking at, because it takes a while for the birds to land on the field. So we could use multiple seconds to build up this probability. This could also be part of this framework, that you build up your belief over time. But it was not a part of the paper, but it could be part of the framework.
So with, I guess with results in the 90%, if you built that up over time, you would expect that to be pretty certain.
These results here, they of course show that the model is capable of performing what we want to do, but the important results are when we decrease the signal-to-noise ratio, because that's the really practical scenario. And of course, if you add different kinds of noise models on that, different kind of background noise, you could get a more realistic perspective of what you need to achieve.
Okay. Thank you. Could you turn to 46? Yeah, that figure, that's the one.
Yes.
So you mentioned in your thesis, talking about the fitness, how good your estimate is of the position. How good do you expect it to be? What's required, and where does your idea of goodness or badness for this?
Well, the application is recognizing behavior. So this is this paper about arrays is getting some of the fundamentals for later on trying to recognize behavior of these. So I don't really know to what precision you need for the tracking, but of course you need to be able to say that the birds are flying in a specific direction, and maybe also with a specific velocity, because you want to see if they're slowing down or if they're just flying by. Because if they're flying by, you don't really need to apply the stimuli, because then they're just not landing on your field. But I don't have any theoretical boundary what I should achieve. It was the paper was more to show the framework and show that we needed to improve the tracking when we experience these kind of wind gusts and background noise, and how could you do that with using very few sensors.
Okay, and while we're also there, the microphone arrays, let me give context to this question. If you have a single box with your actuator, your scaring mechanism, and your microphone, I could imagine that would be fairly easy to deploy. The farmer sows a field,
Yes.
and he pulls it on his tractor and leaves it there, and away we go. But putting microphones all the way around the edge suddenly becomes more of a logistics problem for the. How much benefit do you think the array brings over the single microphone approach?
Well, I also mentioned this in my presentation, that it would complicate the infrastructure of this system, of course. One thing is that one system, it also has a limited range for the microphone and also the speakers. So if you have a very large field, you would still need multiple systems to cover the entire field. So in that aspect, you would need some kind of multiple sensor setup. So the gain here, or the complication here, is of course getting these devices to talk to each other and then collaborate on that. So in aspect, you would expect to use more devices on a field, and you could just easily use the information from all devices at the same time.
Okay. So, just a little forward to page 52. This isn't so much about the audio. I was just curious about this. You had this chart also in your presentation.
Yes.
So you went on 3 transects.
Yes.
Out in different directions, and
Yes.
you'd count the
The way you do this is you go out, let's say 10 meters from the system, and then you have a hula hoop, and you throw it like 3 times, and you count the droppings within the hula hoop. And then you go out 20 meters and do the same again. And then it gives some kind of measure on the activity. We had biologists helping us with this way of evaluating.
So why do you think that at 10 meters, why isn't the green line almost horizontal?
Well, this is because we have something called an edge effect. So the system was placed in the edge of a field. And you see, even though that especially in this case, geese are very insensitive to a lot of disturbances. They really like to be in the center of a field and not go towards the edge, because there could be danger on the edge. So, and also in this specific scenario, we also had some water on the center of the field, around 40 to 50 meters from the device. So that was a very attractive area. But the general rule is the longer away from the edge, the more activity you see, even if there's no scaring device.
Okay. In your presentation and in your thesis, you make good arguments for avoiding or reducing habituation by using these very specific approaches. Those are hard to quantify, I guess, with just a little bit of data. But talk to me a little bit about how you think that will work and how you might quantify or prove those results, if you were to continue this work.
To show that you would less pronounce your habituation?
Yeah. To show that, let me back up. 2.14, that seems to show that you've got something that works. Let's see, 2.14, which was that?
52.
Yeah, system turned off. Yes. So, I guess maybe I'm hoping you can just put me at ease a little bit.
Yeah.
And my unease comes from making a claim, although it appears to have some basis, that your system will help long term and avoid habituation. Do you have any idea that this would be an indefinite, a perfect solution, or it could be, or do you expect it, the geese to eventually habituate to this? Can you just put me at ease a little bit more?
Well, the reason that the geese habituate is that there are of course many factors, and we're not sure that we covered all the factors using this, of course. But some factors that we know is that if you apply stimuli continuously or even random trigger, that over time you would see habituation. So this system, it's designed to only apply stimuli when they're actually there. So that's one thing going towards that we could extend this period. The other thing is that when we detect the geese landing on the field, that's the time where they're most alert. So if you could trigger your scaring to that specific time, then you have a high probability of success. We also see that if you take an existing scarecrow and you put it in the field for, let's say, 1 week or 2 weeks, and you see the birds getting used to that scarecrow, if you manually go out and move that scarecrow, then you prolong the period of this being effective. So you vary the scaring in a way. And the way that this framework is designed is that it's able to recognize that this species is having this behavior in this area. And if that behavior changes towards being longer time around the system, then it should vary how it scares away the birds. So this could be done using natural predator sounds. It could also be done just using what we use now, which is large bangs or dogs barking. But the important thing here is to vary the scaring. But to say that this is the holy grail, well, we need more information, we need more field experiments, as I also shown. But we know that they can habituate to the bioacoustic signal, which is the most promising signal. But they're less likely to habituate to this, and also because some observe that if you have a system playing bioacoustic alarm and distress signals, they will only go to that area if it's really attractive. So there are several factors, and maybe the attractiveness of the area and just the need for hunger could just rule out any kind of scaring that you just need to go there and eat as a bird. And maybe it's not that easy to defend against that. But if you could reduce the damage to the crops, then that's a really good help.
Okay. I had a few other questions, and you did a good job of addressing some of them actually in your presentation, so thank you. The one last, with limited data, it's always, and you and I guess, are both working in areas where limited data is one of the problems. But with limited data, it can be, overfitting can be a big issue there.
Yes.
Tell me what you've done, or why you think you've avoided that problem.
Well, both with the work with the Gaussian mixture model, but also with support vector machine, I tested these models with the cross-validation. So I split the data using 5-fold cross-validation. So I split the data into 5 chunks, and then trained on 4/5 of the data and tested on the last chunk, and then random, and then did that 5 times with different chunks of data. So that's one way of evaluating performance and not testing, or not training and testing on the exact same data. But of course, it's as you said in your previous presentation today, it's the same birds. But in the case with the acoustic behavior recognition, the data was recorded over 2 different days. So it might not have been the same birds. We don't really know. So that's some of the things I've done to try to avoid overfitting.
Okay. And then I think I have just one other question, and it's more on the thermal imaging.
Yes.
And I don't think you can turn there if you want. My question is, how is this affected by the weather? You know, ambient temperature and such.
Oh, the ambient temperature. Well, of course, if the ambient temperature is high, then the difference between the temperature of the animal and the temperature of the background becomes less, and it could make it harder to detect the animals, especially if the animals are hiding in dense grass, because then, well, it could be hard to see. Actually, as you talked about the data we use for the recognition of the animals, we recorded that on 2 different days, and the weather these days were very different. One was cloudy, and the other was very sunny. So we experienced both cases. And if you have sunny weather, which is mostly the case when you do these mowing operations, you will have that grass patches of dirt or stones or molehills would be heated by the sun over time, and you would have a very hot object that might resemble the temperature of the animal, and therefore you could not only just use the temperature to see if it's an animal or not. And then there's also some properties of the animal, because the feces that we want to detect, they have a feather coat, which has the property that the temperature cannot get through. It isolates them. So here, what we really see is the head and the eyes. That's the easiest part to detect. But as we also saw in the video with the chickens, we're still able to see that it's a hot object. But it could be violated if it's very hot outside.
Thank you.
Okay. I think we're just Technical University of Denmark doing research in computer vision. To ask questions and talk to Kim, please.
Well, thank you very much, and I would like to start to congratulate you on a thesis well done. That does not, of course, mean I don't have questions.
Thank you.
Just to start, while I was hearing your presentation, it just dawned on me. You're saying that we should watch out for having dead animals in the corn, because the cereal could be contaminated if we wanted to use it as animal fodder. I'm just thinking, well, I ate cereal this morning. Why am I not?
It's during mowing operations, so it's actually the grass that we're using for the livestock.
Yes.
And you have seen incidents where maybe when you drive in the tractor, I haven't really experienced myself. I'm glad I didn't. But if you can actually hit an animal and not be aware of it.
Yes.
So you could get.
Yes, but I'm aware of that. Yeah. But my question is really, why is it only livestock that can get bacteria infections? Why did we not include humans, or is that just me?
We have seen incidents where you can trace it back to a cat, carcass of a cat that has been infecting the livestock and with the botulism. So the threat is there that if you run over an animal, then you get these bacteria that infects the livestock. But there's also been some discussion, and I don't.
So still alive, Kim? Good. No, this is not really my field of research. So maybe I should not ask questions, but I think I will anyway. And you'll be over with me if I ask some stupid questions here. No, but anyway, I have just one question. I have a couple of questions, but one question that came to my mind. during your presentation. It's a very practical question here. So we have this scaring device for getting the goose to go away from your field. But where do they go?
Yeah, that's also, they need to feed, of course. So they would go to the field that's closest, where it's still good and where they're not being scared away. But this part of scaring away these large flocks of birds. First of all, there's a lot of bird populations, including the geese, which have grown exponentially. So the population itself is too big, so to speak. So so they are feeding on a lot of farmland. But what we're trying to do, especially here in Denmark, but also in Norway, is to select fields where they are allowed to be, and then we have the agricultural field where they shouldn't be, right? But right now we're experiencing that they are both places because there are so many. So I guess the answer to your question is that they will just go where there's food, and of course it has to be a collaborative solution to the problem, or yeah, it shouldn't just be the neighbor's problem.
Exactly. Okay. No, but in fact you also there answered my next question, which was about, and it's maybe the question I ask it because I'm not very familiar with this field, but what about decoys? What you're telling me that you can do that,
yes.
Try to make the wild stock go, or not the wild stock, but make the
you actually make very attractive areas where it's very nice for them to be, but they still seek out.
Okay. So another question I have, and it's maybe to put some perspectives on your work, and Henrik and David have already addressed it, but I would like you to give me a few words about transferability of your methods, because you have now mainly worked with goose here. So what about other kind of animals? What about other kinds of farming situations, stuff like that? So what is the transferability of your results?
Well, I've mostly been working with, if it's the scaring of the birds here, I've mostly been working with acoustics, of course. Just this one. Of course, you're limited to the animals that vocalize, but this is a fact for all these major bird flocks that we are dealing with in agriculture. So that's not the big issue. And as I said here, this could be a very generic framework. So the way you put it here is that you have concatenate data from all your conflict animals here to make the system able to recognize between the animals that you want to address. And then you have different models for these animals here. Maybe I've been working with these 4 species right now. Maybe if you have 6 or 7 other species, then you see that maybe you should choose, of course, different parameters for your model. But maybe the Gaussian mixture model is not the best model right now, but it could be another model. But the framework is still able to distinguish between those. And the reason for using Gaussian mixture models in this context is because we want to recognize who is speaking and not what they're saying. So this is also the context in human speaker recognition, where you can train classifiers on more and more speakers and make a system able to recognize between more and more speakers. And it could be the same kind of approach.
That's fine. In your presentation, a very good presentation you gave here, you talked, it was about the mowing situation, not the scaring of the bird. But you talked about, showing these thermal images, and talked about this false positive situation. And you can say that's perhaps the most, or the best of the situations, because you say there is an animal, but that's not. But what about the opposite would say false negative.
Well, that's not a good case, of course, if you don't discover the animal. And we saw that when the bird or the chicken was covered in very dense grass, or if they're hiding in very dense vegetation, then it could be a problem to detect them. And that's also why we investigated using this top view image, because you have a more clear view, of course, but you could also have the drone fly closer, so you could get more and more visual information, rather than when you're mowing with a tractor and you have to do it right now. So maybe you hit or maybe you don't. If you don't see it, then you possibly hit, right? So if you can build up some kind of certainty that we're actually seeing an animal, then that could aid in with respect to false negatives.
But in the field experiment you conducted, you didn't didn't run into some false negative situations where you weren't able to identify the animal.
Yes, we did. And that was mostly the case when we were very high altitudes, because the objects become very small and we have limited resolution on the camera. But when we come closer, we could see some detail that there was in fact a hot object there. Of course, we didn't put a table over the animal. We made the situation so the animal was hiding in the grass, but not covered with a surface that we couldn't look through.
Yeah.
As would be expected in real life situations.
Yes, of course. They will not be in a cave there. Anyway, maybe I can ask if some of the supervisors has a question. And do you have some questions?
Well, yes, maybe a small one. So Kim, I know you're very fond of classifier fusion. Well, the paper, on audio-visual recognition, we use classifier fusion to fuse the results from the sounds from the microphones and from the cameras, right?
Yes.
So that works quite nice. Now I think we're in a very similar situation, because in the new setup where we try to detect animals in the field, we use thermal cameras and we use RGB cameras.
Yes.
I don't think anybody of us has yet decided whether we should use the same approach, that is, extract features from the two different modalities, image modalities, and then make the classification based on the features alone, or we should classify and then make classifier fusions. So my question here is just, could you give a quick answer to what you suppose is best to do here? Should we classify and then make classifier fusion afterwards, or should we use the other approach? What is your expectation? What is best to do?
I think that we should take some of the good properties of the thermal camera, that we are able to detect these hotspots. So we could, instead of trying to calculate, trying to detect and calculate features in the visual domain, we should wait for the thermal camera to detect which hotspots or which objects in the visual image that we wanted to try to classify. So first we have a kind of a binary mask in the visual image, that these objects are of interest, and you should calculate features in the visual domain to enable recognition of these objects. And this could be based on classifier fusion, of course, because the good thing about the classifier fusion is that you could design classifiers for each problem. So you wouldn't need the same kind of classifier. But there are different ways of dealing with classifier fusion at different stages of the classification. So I can't give an answer to what you should do when you have calculated the features, but I think that when you detect the object in the thermal camera, you can use that information in the visual image. That's the first step.
You suggest that we do the detection based only on the thermal cameras, and then use that to make further analysis in the RGB.
Yeah, further analysis in both images. Yeah. But if it should be in one algorithm or two algorithms working together, I
just a small final question. I've never considered before today, but But how about ranging these devices? So what are really the range? So you had this about the droppings, you were addressing that, David. So what is the range for the, so how many devices do you think is needed, say, a square meter or a square?
Well, that's the frightening devices.
Yeah.
Well, in our experiments and also our later experiments have shown that from up to 250 meters we can detect these sounds. They're very easily detectable when they're flying up in the air and trying to land, or just flying over. You can really hear them. And the range of scaring, well, of course, the sound pressure that you apply on the microphone, on the speaker, could be affected by wind, both negatively and positively. So it's hard to say the limit, but of course you have a limit on the sound, how it attenuates over time, and then you can reverse engineer that and say how sensitive is a goose to sound, at what sound level should we apply for it to hear it. There's also some suggestions that using bioacoustics you can apply sound at much lower sound pressure level and it will still be frightening for the animals. Rather than you use a large bang from an explosion, you can use maybe lower sensitive, lower sounds when you use bioacoustics. So if you use a combination, then it's also really hard to predict. But in the range between 200 and 300 meters from the device.
Okay, Kim, thank you. Just a short question, but first of all, thank you very much for illustrative and informative presentation. What I think could be interesting to elaborate a bit on is taking a commercial aspect. Now you touched upon different methods in your image analysis from the thermal camera. If you should look to the perspective of how to commercialize and where the robustness of the software versus the cost of hardware, where could you see which methods in relation to the cost of hardware, if systems like this should be commercialized? How could you see the software methods being rated in that context?
You mean between recognition and the just detection? Or?
If you want to have the detection, a robust detection system, but knowing that cost is a major issue, we expect that hardware, the resolution, for example, from a camera, and how many pixels you will have per animal, or what you would need. Where could you see the biggest potential for these methods that you have tried until now in relation of the ability to reduce cost on your hardware?
Well, if you have a tractor mounted system and you want to cover the entire working width, you need multiple cameras because you need to cover the working width all the time. So there's a cost on every single camera there. And if you have a drone-like setup, you just need one camera and it could scan the entire field. And of course, you spend a little more time on each field because you need to scan the field. But I would say that if you want to have a bit of certainty in detecting these animals, even though they're hiding in very dense grass, then the drone solution, you only need one camera. Of course you need the expense of a drone, but the market right now is the price of a drone is very low, and the computation that you need to detect and recognize these objects in a thermal image, if you don't use sensor fusion, leave that out of the equation, then that's not really that high computation. You don't really need much computation to do this. So there's not a lot of cost on that part of the drone. So it's only the drone and the thermal camera. Whereas, and that drone could be used on multiple fields over a course of a day. Whereas the tractor mounted system, you would have multiple cameras attached to that specific device, and you will either have to move the cameras to another device or just a very expensive one device. So I hope that answered your question.
Thank you.
Okay. Well, in the break I didn't receive any questions, but we pick some up now. I don't, but still possibility to ask Kim a question if anyone from the audience would like that. Doesn't seem so. So I think this brings us to the end of this public defense, and I think first of all we should give Kim a big applause here. So now this public part is closed, and I would like to remind you that we have a reception down in 101, and you're welcome to go there, and the assessment committee, we will come down there later after we have discussed what's been going on here. So thank you.